I'm honored to be here and to give this class this morning. So I was told that the audience is broad, so I also broadened up my presentation. Um, I will uh, I will entertain you with some hot topics, recent hot topics such as AR, VR, but also about the metaverse. I'm sure some of you might have heard that name recently. So
Okay.
let me share my screen. Can you see my screen?
Um, it's coming.
Yes.
Yes, not exactly. Now is okay. It's okay. So
Okay,
Bernard, we are in hybrid configuration. It means that we are some people are online and also some students and people are in this room. Okay.
great. Thank you.
Okay. So thank you again. You have
Thank you. So,
you have the screen for you.
so I think I have an hour, right, Eve?
Yes. Yes.
Okay, great. Thank you. So the title of my talk this morning, this afternoon, sorry for you, this morning for me, um, is how AR, augmented reality, VR, virtual reality, and MR, mixed reality, hardware are enabling the coming metaverse. Um, I'm talking more today with my SPIE hat rather than my Google hat. Um, So first of all, if you want to know more about this field, there are two conferences annually around. You can participate. The first one is Augmented World Expo in Santa Clara, California. That was just 2 months ago. It's mainly focused on experience, not so much hardware, but experience around mixed reality. And then the second one is an SPAE conference that is going to happen in 2 weeks. I'm actually chairing this one, and this one is dedicated to hardware. So we started this series of conference about 4 years ago, and it really gained a lot of traction among the community around mixed reality hardware. Um, Students, industries, startups, academia, but also investors. So I know any conference since the start of the pandemic is challenging, um, but we still decided to this year um, to go on with a full in-person conference. People are longing to meet in person together, uh, and um, and we'll see how that goes. That also is a catalyst for the metaverse, for trying to bring people together virtually in a setting that is way more connected, that has a sense of presence um, um, much greater than a 2D computer screen over which I'm looking at and over which most of you are looking at. So we're going to see how the metaverse might enable future conferences in a much more immersive way. So what is a mixed reality spectrum? Well, it's basically a blending of the physical and digital world in which users may interact with digital and real world objects while maintaining a presence in the physical world. And this is really important. So that's not VR, that's mixed reality. But VR with video see-through can also implement, such a sense of presence. Mixed reality is really the third wave of computing. And we started in the 70s with personal computers. Then in the 90s and especially 2000s, we went to smartphones. And today, obviously, we have a much broader choice through the intelligent edge that is connected to the intelligent cloud, which comprises many IoT Internet of Things, and many devices, including your car, including your home, but also including wearables, and wearables such as augmented reality, virtual reality, mixed reality, and smart glasses. We're going to talk a lot about smart glasses today. So let's talk a little bit before we go into hardware. Let's see where these devices, these wearable devices, might be used in each case. First, we're going to start with the industrial case, the enterprise case, and then we're going to see where these devices are used in defense. And defense historically was the first application ground of augmented reality and mixed reality headsets in the 60s. It's always the army that starts. The army started DARPA, obviously, which became the internet. Army also started mixed reality in the 60s for fixed wing and rotary wing aircrafts, and also training. So let's go first to industry, because that is a domain that resonated more with mixed reality hardware. By 2030, that's in about 10 years, 8 years, mixed reality has the potential to deliver 1.5 trillion boost to the global economy. Now, of course, that was before the concept of the metaverse was initiated. That market of 1.5 trillion could actually get up to three or $3.5 trillion with the metaverse. In industries, mainly enhanced training, risk reduction, faster product design and delivery, and to talk about a few numbers, product and service developments, about $350 billion. Healthcare, same amount. So you see that these are the two main pillars. And then development and training, a quarter trillion. Process improvements, quarter trillion also. And retail and consumer, about $200 billion. Mixed reality is really and the first anchor of mixed reality is really enterprise. And enterprise, enterprise trying to get to the standards of Industry 4.0 in a few different fields. First, remote collaboration, which is very important, and it's even more important in a pandemic. In a pandemic time, where human travel is limited. Guided training and task management is also one field that has been catalyzed with the pandemic. Training and simulation, remote training, again, is also one of these fields that has got a terrific boost in the pandemic, and there's no wonder why the concept of metaverse was actually introduced after 1 year of pandemic. Sales assistance, design and prototyping, and contextual data overlay. And these are traditional applications of mixed reality. And really what is important in industry, mixed reality, the real return on investment for mixed reality is cost avoidance for the enterprise. Okay, so and during my time at Microsoft from 2015 to 2021, we worked a lot on industry applications with a hardware that you may have heard about, HoloLens 1 and HoloLens 2, and we're going to talk about these two headsets in more detail towards the end of this class. Mixed reality use in defense. Let's talk a little bit about defense. I told you that everything starts with defense, and not everything stops with defense, but defense is a real good catalyst. So in 2018, at Microsoft, we got the first contract for defense applications with a dedicated mixed reality headset. It was $500 million and we thought that that was a great contract. Um, 3 years later, in 2021, early last year, the Army came back with another ask, and that was development of a series of headsets for planning, training, enhanced vision. Of course, this is low light vision and also far infrared thermal vision, superimposed on your reality, and also leveraging data for $22 billion over 10 years. So that's the largest the largest purchase order. It's not really a purchase order. The largest contract uh, ever in the field of MR, AR, and VR. Um, there has been a few setbacks. I'm not going to talk about the setbacks. There's always setbacks in hardware that is difficult to implement, as we will see later on. There's a lot of nitty-gritty details in the optics, the display systems that need to be solved. But I think that that vision of the U.S. Army and really any army will continue. So we talked about industry and defense. Let's talk a little bit about consumer. But a consumer, you have to ask yourself that question: what comes first? Is it a use case? Is a epiphany? Oh my God, this is the use case. Let's implement it. Or is this hardware? In this case, you would say, let's polish a nice pair of smart glasses. We don't really know what the user is going to do with it, but let's have a nice hardware, ship it out there. Consumers will buy it, and developers will know what to do with it. Well, the reality is a little bit more complicated. Um, the use case didn't come first. We have a very good use case for these guys here, smartphone, but the use case for smart glasses for consumer is still a bit of a question. So Google Glass, 10 years ago, we started Google Glass, and we uh, we developed a hardware that was quite polished and nicely integrated, and didn't really resonate with consumers. Was actually got actually a negative spin to it after a couple of years. And Google Glass 2 and 3 were reoriented solely to enterprise, and that really resonated. So smart glasses did not resonate with the consumer 8 years ago. With HoloLens 1 in 2015, actually it was January 2016, uh, we targeted HoloLens 1 both to enterprise and consumer, and there was pretty much no echo with consumer because there was no use case. The use case for enterprise, as I showed you before, were custom applications that were developed by every single enterprise. So every single enterprise has a very specific need, and the fact of buying the headset is just the first step. Then comes the development of the custom application use case that this particular industry will need through that headset. That's not going to happen with consumer, because consumer need generic applications, generic use cases. I hate to talk about killer apps because it doesn't really mean anything, but generic use cases for consumer. And that's not easy. So one question that you might have is what went wrong with the first time with smart glasses? Not only Google Glass, but I'm thinking about companies like Meta. Yeah, Meta, 7 years ago, it was called MetaVision. Nobody knew what Metaverse meant at that time. And they provided consumer smart glasses, consumer mixed reality headset. The company went belly up after a very good investment round. Another company, ODG, which was mostly linked to defense and then went to enterprise, also went belly up. Another company called Daiquiri also went belly up, and a few others. But recently, and this is end of 2021, recently we started to see a resurgence in discussion about the topic. A lot has changed on the tech front, and we'll see this. Society seems to be in a better place to accept this trend now. Well, I would put a question mark there. With that in mind, can we realistically expect smart glasses to actually take off this time around? Well, Microsoft earlier this year introduced the concept of mesh before Facebook introduced the concept of metaverse. So it's a concept of bringing people together virtually and really providing the sense of presence. Presence is really everything. Having the sense of the presence of another human being around you, while that human being physically might be located a few thousand miles away. So scanning the entire body, but also scanning especially the expression, the face expression. And when I mean face expression, I mean the eyes, the mouth, and the forehead. And that pretty much defines your whole body experience. The rest is just gesture sensing and reconstitution of your body through artificial intelligence in the cloud. Other companies like Magic Leap proposed new hardware and also concepts such as C3, communication, collaboration, and co-presence. They also got another round of $500 million investment last year. And Magic Leap 2 came out with a field of view. So this is an optical see-through device, similar to a HoloLens with a field of view that is much larger and doesn't have a landscape form factor, but more a portrait form factor. Just because we're living in a vertical world, most of us are vertical, and makes a lot of sense to have a one-to-one aspect ratio in the display, or even a portrait aspect ratio rather than a traditional monitor landscape aspect ratio. So that was 70 degrees. It was based on the LCOS system and diffractive waveguide, which we'll talk about later. French companies also. This is a company in France, Lynx. I know the CEO pretty well, Stan Larocque. He was a laureate at our first optical design challenge at the SPIE. We had optical design challenges for students to bring students in contact with industry, and actually that went pretty well. So that student, got a prize in our first optical design challenge that we created with various companies, including Amazon, Apple, Google, Facebook, and Microsoft, and that gave him the entrepreneurial fiber. And he went on to create a startup right after his studies. And now I think he has 20 employees or so, and is developing a state-of-the-art video see-through. That's not optical see-through, it's a video see-through mixed reality headset, specifically dedicated for enterprise. With very original lenses. You can see the lenses there, which reduce the form factor of your traditional VR headsets. You may remember traditional VR headsets from Oculus, which is now called Meta, or HTC Vive, or Sony PlayStation VR, and they're quite bulky. So today there's a trend to reduce the form factor. And reducing the form factor is basically working on the air gap between the lenses and the display. You may have heard about Facebook's first smart glasses, which don't have display. It's an audio only smart glass, and it's still unclear, how much traction these glasses have from consumer. Now, of course, one thing that was very, very interesting with Facebook is that they define these glasses as Ray-Ban glasses, and they're sold by Ray-Ban. So Facebook doesn't appear anywhere. I don't know about you, but I wouldn't feel comfortable walking down the street with a pair of glasses where Facebook is written all over, for many reasons. So that was a very smart move. And I have a pair of Ray-Ban stories, and I use them for many conference calls. but again, there's no display there. Apple also is working on a AR VR headset, but with Apple, it's difficult to find out what they're really doing. Um, but what we know is that video see-through mixed reality headset at 8K resolution might come out this year, and smart glasses might come out in a couple of years. They will both be linked to, of course, an iPhone. So companies that provide a smartphone, such as Apple, such as Google, and Samsung, would prefer an architecture uh, of a smart glass linked to a companion phone for the processing. And companies that don't have a smartphone, such as Microsoft and Amazon, while these companies would prefer smart glass as a thin client directly through 5G to the cloud, to Microsoft Azure or Amazon cloud services. With the upcoming metaverse is not only relying on wearables to provide an immersion, um, a sense of immersion. Google also developed a light fields display and a 3D scanning display that will allow you to communicate in the pandemic era, but also in the metaverse, um, through this device that you see here. Now we don't know too much about it, but it's an immersive display with speakers, a microphone, depth and RGB sensors capable of capturing roughly 180 degrees of the subject and algorithms to fuse the data from multiple sensors into real-time 3D model of the subject. Other companies such as Lightfield Labs in San Jose here that got a lot of attention recently and provided also a different technology, a different light field technology. There's also another company here in the valley called Leia. Actually, the founders are from École Polytechnique, and they developed a very interesting light fields display concept, which is based on diffractive backlights, directional diffractive backlight. And they unveiled a second version at the CES this year, the LUMPAD 2. I advise you to look at this. It's a US startup, but two French entrepreneurs from École Polytechnique. Okay, let's talk a little bit about the metaverse. That's the amount of hits on Google for the word metaverse. So you see that not really anyone was bothered by the metaverse before end of last year. And end of last year, suddenly everybody talked about it. So what is it? Well, you can look at the Gartner cycle also, and the metaverse would be right at the top of the peak of inflated expectations. Um, and let's see if next year or in 2 years, the metaverse will still be there, but not at the peak of inflated expectations. It might have gone through the trough of disillusionment. That will happen. And sometimes these technologies drop off the Gartner cycle and you don't hear about them for another 20 years. And that happened with optical computing in the 80s. I think Pierre Chevelle can talk about this in length. It was a big boom of optical computing in the 80s and the 90s, and we're just starting to talk about this again. Maybe the metaverse will make its way to the slope of alignment and even go to plateau of productivity in a few years. Who knows? So from Wikipedia, the word metaverse is made of the prefix meta, and we talked a lot about meta optics, meta surfaces, but also meta vision, and the stem verse, which is back formation of universe. So it's a concept of a future iteration of the internet made up of a persistent shared 3D virtual spaces linked to a perceived virtual universe. So immersive displays such as AR, VR, and MR are perfectly adapted for this. The concept of Metaverse was introduced originally by Neil Stephenson in 1992 in his sci-fi novel Snow Crash. I advise you to read that novel. The first movie about the metaverse, and was not called the metaverse at that time, was Ready Player One in 2018, which is a sci-fi depiction of a VR metaverse in 2045. Most of the action unfolds in a vast network of artificial worlds called the Oasis. Now, some key aspects of the metaverse spans the physical and digital worlds, and that's exactly what mixed reality headsets are doing. It's always on. It's a real-time world in which an infinite number of users can participate simultaneously. And I'm sure you're thinking about some games today, but it's going to be way more than gaming. It also incorporates a fully functioning economy based on cryptocurrency and other aspects such as non-fungible tokens, NFTs. And that's just the tip of the iceberg. Games, well, I'm sure you know about Fortnite, Roblox, and others. My kids are too much fun about these games, but these are some of the first games that take advantage of the metaverse. Now, of course, one person who wants to take advantage of the metaverse is Mark Zuckerberg. Since last year, he's planning to hire 10,000 engineers in the European Union to build a metaverse. So prepare your resumes if you want to work at Meta. Facebook also plans to rebrand, and they've rebranded their company name in October last year. So the question is, if you remember, Facebook was in a lot of legal trouble last year. Can the metaverse save Facebook? Maybe, maybe not. There's already a battle to control the metaverse, Microsoft versus Meta. Microsoft mostly on the industrial metaverse, and Meta obviously on the consumer metaverse. One of the first example of Microsoft was the implementation of Microsoft Teams, which enters the metaverse race with 3D avatars and immersive meetings. Immersive meetings are can be way more interesting and way more neutral than regular meetings in person, but also meetings over Zoom. Adobe is another one that looks to collaboration, the metaverse, and NFTs, non-fungible tokens for growth. Nike, is another one. Gemini is another one. Samsung, Adidas, Unity, and even Disney is banking on the metaverse for the future, and Nike obviously also. A few vocal voices in the field of market analysis, Katie Wood, are touting that the metaverse could be worth trillion. So at the beginning of that course, we talked about $1.5 trillion for industry. Now, when you count the metaverse, consumer metaverse, it's a few trillions. Who cares? After a few trillions, you don't count anymore. So Wood is not alone in our prediction that the metaverse could prove to be lucrative. Epic Games CEO, same thing, and Bloomberg, thinks about the same also. So there's chances that it will happen. So 3 months ago, everybody talked about AR, VR, MR, and social networks, and today everybody still talks about AR, VR, MR. We have our conference coming in. SPIE conference coming in 2 weeks on the hardware type of AR, VR, MR, but really everything is served with the metaverse source today. Between you and the metaverse, there is hardware, and that hardware spans from virtual reality to augmented reality, and also to legacy gateways such as phones, laptops, and we talked about light field displays, which is really, really interesting. light field displays on 2D tablets. So back to hardware and the various challenges in attempting to build the right head-worn device, which looks like this in the movie Ready Player One. But we know that real hardware already looks like this today, and this is again in the Lynx One headset from the French startup Lynx. So it's very close to what was depicted only 3 years ago in the movies, to have this ready today as far as the hardware is concerned. So let's talk about, oh yeah, and you know, when we're talking about uh, the the challenges in optics and display, well, there are many, you know. Optics, well, we need to talk about optical combiners, waveguides. They can be geometric or diffractive. We can talk about bird bath, free space optical combiners, 2D collimators for VR, hybrid Fresnel lenses, meta lenses, 2D lenses, and then displays, micro LED, micro OLED, but also micro LEDs, micro inorganic LEDs, laser beam scanner, LBS, LCOS, liquid crystal on silicon, light field displays, and of course micro OLED, advanced LCDs, and light field displays. Sensing and haptics, very important. Time of flight cameras, micro cameras, flexible strain sensors, microfluidics, electroactive polymers, and other related technologies such as, of course, flexible batteries, transparent antennas is very important. Computing systems, lightweight, high refractive index glass, optical meta materials. So let's talk about display challenges, brightness and low power. Well, what do people use today in devices since a few years? Micro organic LED arrays, which provide 1 to 2K nits, which can be used with a free space combiner, such as a bird bath that is used in the Nreal smart glasses. High temperature polysilicon backlight LCD, the one that was used in Google Glass V2. Front light LCOS. This is an LCOS. An LCOS is a reflective display, but can use a front light also. It's basically a backlight, a transparent backlight. Backlight LCOS with the use of PBS, polarization beam splitter cube. This is the one that was used in Google Glass V1. And then micro LED. Micro LED, you know, creates a lot of fuss today. We all know LEDs. You know, they light up our streets, our homes, our cars. But what about if you start to shrink the size of the LEDs to just a few microns, let's say 2, 3 microns? Well, the quantum efficiency of this, the internal quantum efficiency, especially the external quantum efficiency of these LEDs, starts to drop. Now the game is to increase this quantum efficiency beyond what a flat LED can do, and companies are gaining a lot of traction, such as Alidia in Grenoble. They raised 120 million euros last year to develop exactly this micro LED arrays with epitaxial layer deposition that can not only provide a band gap for one color, let's say green, but can provide a band gap for green, blue, and red at the same time in a 2K micro panel with pixels up to 3 microns or so. Backlight DLP are digital light processing. These are the micromirror arrays. These are not MEMS scanners. Micromirror arrays can provide up to 700 nits, 700 K nits. Sorry, there's a K missing there. And then free space LCOS, free space illumination with Osram LEDs, for example, of LCOS system that was used in HoloLens 1 and Magic Leap 1 and Magic Leap 2. Provide 1.5 million nits. These are nits at the display, not nits at the eye, because that would burn your eye, that's for sure. There's a waveguide in there, which is the big nits slasher. Go from 1.5 million nits at the display engine to about 1,000 nits at the eye. LBS, laser beam scanner, can produce 2 to 3 million nits, and that was used in HoloLens 2 and free space DLP, which is for the moment the strongest display option. But you see that micro LED has the option to be the strongest display option with the smallest packaging, because it's an emissive display. There's no need for an illumination system. Micro LED panels, well, the ecosystem is building up. You need 3 areas of expertise. You need silicon backplane integrators. You need LED epitaxial growth, single color or 2 colors on sapphire wafers, like it's done for, most of the LEDs. But really, what you want to do is to grow your epitaxial growth, gallium nitride, gallium indium nitride, or um, oil and gas on silicon, so that you can combine the LEDs with the backplane, which is usually done on a 12-inch silicon wafer with a 12-inch wafer bonder. Wafer backend process, very important. You need to tune the emission angle. Well, first you need to transfer the LEDs on the backplane, and then you need to tune the emission angle of the LEDs, which are Lambertian, to something that is a little bit more narrow to provide a good contrast in a light engine. That can be done with a micro lens array, but also with arrays of photonic crystals that are etched on top of the LEDs. And these are usually these custom transfer process startups that are, that investors love to invest in. But you also need the industrial strength of the LED epitaxial growth with MOCVD machines and the silicon backplane integrators, which are usually the older LCOS manufacturers, because they know how to design a highly efficient backplane. This is the light engine that is used in HoloLens 2. It's a laser beam scanner with two lasers per color and some reflective relay optics in between, fast scanner and a slow scanner, MEM scanner. So let's talk about optical combiners. Small form factor, high efficiency, great image, and low cost. Well, here you have a few. I'm not going to enter into details. We look at the Epson Moverio, Google Glass V1, Zeiss tools, Lumos, OptinVen, which is a French company, again in Rennes, Latin AR, a Korean company. And here is an example of how Zeiss implemented their curved waveguide. There's no pupil replication in there. There's one pupil in, one pupil out, so you can curve your waveguide. And this is done by a total internal reflection. The waveguide is butt coupled to the curved substrate, and there's not going to enter into details, but there's a low index glue between the prescription lens and the waveguide, so they form a single plastic shell. Pin mirror technology from Latin AR in Seoul is very, very interesting. The display is butt coupled again to a waveguide, which in this case is planar, and there's a series of mini mirrors, not micro mirrors, but mini mirrors, and there's a little, I call it a smiley face. The smile underneath is actually a bird bath reflective lens that collimates the field from the display and then shoots it up again. And the micro mirrors, the mini mirrors, are providing the different pupils that are entering your eye. And this is a plastic concept. Lumos in Israel and Schott entered into a strategic partnership last year, 2 years ago, to provide reflective waveguides in glass, which are very efficient, much more efficient than diffractive waveguides, and they have better color. But you have to fabricate these devices, which are composed, as you can see here, of laminated pieces of glasses with different dielectric coatings. So it's a bit complicated to do. A lot of companies, smart glass integrators, are interested in diffractive waveguides, and Snap acquired an AR startup in the UK, Wave Optic, last year. It's basically a design house for diffractive waveguides. you know, for $500 million. It's a crazy world. Pixeligent launched Pixel Clear Titania. We talked about high index of refraction, Corning, and glass makers like Corning. We talked about Schott before. Corning, Asahi, Hoya. They all look at participating in the joining the bandwagon of AR and waveguide. Diffractive waveguides to provide high index substrates, but also high index resin that can be nano imprinted with these diffractives to produce smart glasses with a form factor that is small and that can be integrated on a device such as this one, with field of views up to 30, 50, maybe even a little bit larger than 50 degrees. Short real view is one example. You can see some of the glasses that were cut in the shape of a lens, and then of course the diffractive structures are imprinted by nano imprint on these substrates. Another company in Finland just raised $33 million. It's a design house also for diffractive. So if you took Pierre Cheval's class and you know a little bit about diffractive optics, Fourier optics, and rigorous coupled wave analysis and FDTD, well, you might be able to join that bandwagon also and get bought for half a billion dollar. It's possible today. It's not possible a few years ago. Might not be possible in a few years, but here's your chance. Xiaomi shows off a concept. It's a Chinese company. Concept smart glasses based on a micro LED display. You can see this here. You can see the diffractive elements nano imprinted on the piece of glass, and how the outcouplers are outcoupling this field. TCL, same thing. They use a micro LED display combined to diffractive waveguide. Vuzix, another company in the US that launched their smart glasses at CES last year with micro LED also. Initially it was LCOS and now micro LED. The big difference between LCOS and micro LED is that micro LED is an emissive display and LCOS needs an illumination system which increases the size of the display engine. 2D exit pupil expansion are legion today. They reduce the display engine size because the display engine size only needs to create a small pupil. This pupil is then enlarged by the waveguides to provide a large eye box to accommodate a wide IPD, interpupillary distance, therefore a wide population. Can be done with surface relief diffractives, holographic diffractives like Digilens, or reflective like Lumos. Either in mirror mode operation, that would be smart glasses, or periscope operation, like in AR goggles, where the display engine is looking to your eye rather than looking to the world. These are some of the diffractive structures that I used. Top-down binary SRG, surface relief grating structures, top-down analog mirror SRGs, blaze gratings, slanted gratings, and then, of course, volume holograms. I think Imagine Optics, one of these companies, just got bought by Meta, aka Facebook, a few days ago. Aconia Holographic got bought by Apple a couple of years ago. You see that there's a lot of traction there also in volume holograms. And then reflective waveguides such as a single extractor, like in the Epson Noverio or the Zeiss 2s, reflective glass with multiple mirrors. These are dielectric, not fully reflective, like Lumos, Lingxi, and Orim. And then, of course, reflective plastic with multiple mirrors, either dielectric or multiple small mirrors, like in Latinair or Optinband. Basic concept is this. There's an incoupler and there's leaky outcouplers that create an iBox. Imagine this being a hose in your garden, and you want to water your lawn. You don't have sprinklers. Well, you put holes in your hose, but you have to put small holes first and then large holes later because you want to have a uniform sprinkle of your lawn. And here it would be photons coming out, so that the efficiency of the diffractive elements needs to increase in order to provide a uniform iBox here. There are various operation modes in waveguides. It can be sandwiched, buried couplers, transmissive couplers, reflective couplers, and of course transmissive and reflective couplers that are both working in both directions. Again, we talked about the different type of surface relief coupler geometries. It's a complete zoo today. Blaze gratings, slanted gratings, binary gratings, analog surface relief gratings, or computer-generated holograms. Holographic coupler platforms, it's a zoo also. So these are volume holograms. These are not surface relief gratings, such as thin transmission holograms, 2 to 3 micron, actually closer to 2 by Digilens. Thin reflections, such as the photopolymers provided by Covestro, DuPont, or Polygramma, at 16 to 70 micron, and then thick reflection transmission photopolymers, such as the Aconia, which was bought by Apple, which is 100 to 500 micron thick. These are typical slanted gratings as in-coupler and out-coupler. So, you know, when you looked at this 20 years ago, that could have been an interesting paper at an SPAE Congress. But today, you know, if you can do this in volume, well, you get bought for $1 billion. So it's different times. HoloLens 1, this is how we implemented HoloLens 1, slanted grating in coupler and leaky outcouplers, 1 plate per color. So you have a light engine that provides 3 colors, and each plate processes 1 color, and then of course everything is added, and your eye sees the reconstructed beam. It's a periscope mode operation. And in the Magic Leap headset, it's different. It's a mirror operation, so the eye is on the side of the display engine, and slanted gratings are used as blaze gratings are used as ink couplers. The pupil is separated into 3 different pupils, each one for 1 color to increase the efficiency, and then combined again with leaky binary gratings that have a modulation in the depth to modulate the efficiency, just like in your garden hose, to have a uniform iBox coming out. And you recombine the RGB image. You can do this with 2 plates. If you don't want 3 plates, you can do this with 2 plates. This is the K-vector diagram. You can propagate the entire blue field of view in the first plate and half of the green field of view in the other plate. And then in the second plate, you propagate the entire field of view of red and the other part of the green, and you recombine everything. You can also do everything in a single plate, you know, by coupling the red, the green, and the blue field of view in a single plate with a single grating. But again, gratings have a large dispersion, so you need a very high index glass to provide a wide donut in your K-vector space to propagate all 3 fields at the same time. So what people usually do is they reduce the field of view and therefore can propagate all 3 fields at the same time. That was done with the Sony smart glasses and Dispelix smart glasses. That's also something that you know, was a lot of research was done with metasurfaces that can provide you know, 3 different grating functionalities that would diffract the red in one direction, and then the green in another direction, in the same direction, and the blue in the same direction. So these are angular selective meta surface, aka the diffractive elements, but angularly selective diffractives, which are called meta surfaces. And if you have an idea on how to implement this, that's your chance to get a check of $500 million, if it works. Vision comfort challenges. Vergence accommodation conflict is one of the big challenges in smart glasses, because in the state of the art VR headsets and MR headsets, you have a fixed focus of your image, but the stereo disparity can actually produce the image anywhere you want. So the vergence of your eyes, you can trigger the vergence of your eyes, but the focus of your eyes, you have two oculomotor reflexes that are linked. It's the in the real world, it's the accommodation and the vergence. In quasi all the state of the art VR and MR headsets, the focus is fixed, but the stereo disparity provides vergence, and the difference between the vergence and the fixed focus is called the vergence accommodation conflict, and that can be measured in diopters. And this is a graph that shows the diopter conflict for a display that is fixed at 2 meters, such as HoloLens, for example, or any other VR headset. And if you talk to your optometrist, he might actually tell you that a quarter diopter conflict is okay before you get sick. Others might say that half a diopter is okay. So if half a diopter is okay, if you set your focus at 2 meters, which is half a diopter also from infinity, then you can comfortably look at an image that is provided by stereo disparity. Stereo is really a French pastime for the past 150 years. The Stereo Club de France, had a few tens of thousands of members 50 or 60 years ago. Actually, a close to 100,000 members, and today there's only a few thousand members uh, uh, at the Stereo Club de France. So really, stereo display is a old technology that is actually at the core of the state-of-the-art mixed reality headsets today. We're still using stereo display, but we need to compensate this vergence accommodation conflict in stereo displays. Um, especially if you want, especially if you want to use them as mixed reality, you want to interface uh, um, with the display, just like what we do with HoloLens or Magic Leap. You want to interface with the display with your hands on the display. You want to touch the display. You want to push buttons. You want to move the display around. And usually your arms are only 50 to 70 centimeters long. So you have to be able to, present the image, let's say buttons at 70 centimeter without having this vergence accommodation conflict, and then of course also provide information at a distance. So how do you do this? Well, you can switch the focus, and this is done in Magic Leap 1. You can continuously vary the focus of your image depending on where your eyes are verging with eye trackers, two gaze trackers, and the differential is basically the vergence of your eye. So you track the vergence of your eye, and you set the tuning with fluid lenses, liquid crystal lenses, you name it. But then, of course, you can also do multifocal, which is basically a temporal light field where you present very, very fast different scenes at different depths with MEMS, fast switching lens. You can also do retinal scan display. What is this? This is a Maxwellian display. This is a display that uses small laser beams and traces directly the image on your retina, and the fact that these laser beams are so small increases the depth of focus, and the depth of focus is basically infinite. So the image is in focus no matter where you focus at. This is good because the image is always in focus, but this is bad because it's not reality. Reality is not like this. My reality is, is defocused if I don't focus on it. And we're human beings with a few 100,000 years of evolution, maybe more, and we like to, we're creators of habit, and our visual cortex works this way. So if suddenly you have an image that is in focus, no matter where you look at, you know perfectly that this is a synthetic image. It's not really a mixed reality experience. So it's perfect for text, for example, but not for having a pink elephant sitting in the chair in front of you, because it will not look real. Holographic display, of course, that's the Rolls Royce. It's either holographic display or light field display, and a lot of work is coming along these lines to provide a zero vergence accumulation conflict, no matter where you're focusing at, because the display can provide a per pixel depth. So every pixel is actually located at a different depth. Now, of course, you have to calculate the hologram, the computer-generated hologram in real time, but algorithms exist today on the cloud to do this. Sensors, and this is the last part of my presentation on hardware. Sensor track for universal use cases. Well, you need depth map sensors, and usually depth map sensors come in three different flavors. Structured illumination. I think everybody heard about Kinect from Microsoft about 10 years ago. It was based on structured illumination, a computer-generated hologram that provides a series of spots or lines, and then the deformation of these spots or lines provides a depth map. But today, the sensor of choice is more the time of flight, um, real time of flight, or a phase time of flight, which is used in HoloLens 1 and HoloLens 2, and many other devices. SD Micro is also working on time of flight sensors. Stereo imaging is another one. It's the poor man's depth map sensor, but it's a depth map sensor that does not require specific hardware, but two cameras separated by at least a few inches. Eye tracking, very important. There's two different ways to implement eye tracking. Now, eye tracking can be eye tracking or gaze tracking or pupil tracking or pupil size tracking, which is emotion tracking, or iris recognition. This can be done either by looking at the glints with external illumination, such as in HoloLens 1 and Magic Leap 1 and so on, or can be imaging based. And this is way more precise, but requires much better imaging systems, retinal and pupil imaging. This can be, while a glint can get you to 1 degree resolution in both directions, maybe half a degree. Retinal imaging eye tracking can go down to 100th of a degree resolution, so for different applications. Interesting concepts are also eye tracking integrated in the waveguide. So what you have in smart glasses in front of your eyes, is basically a waveguide, and the trend is to hybridize the functionality of waveguides and not only provide display but also sensing in the same waveguide, and also transparent antennas on these waveguides. A new sensor stack is body and face tracking to enable realistic avatars for your metaverse. So the cloud compute and artificial intelligence can already reconstruct realistic avatars from a simple video feed. Simple 2D video feed can actually reconstruct your entire body if your body is scanned and stored in the cloud, which will be inside in. So in older VR headsets, you had the outside in 6DoF trackers for head locking, for world locking of head tracking, for world locking of the holograms. So you had to put in your first Oculus VR headset some sensors in your room, and then you went from inside out sensing for 6DoF for world locking holograms, and then here you have inside-in sensors. There's sensors that senses yourself, senses your eye, your forehead, and your mouth expressions to provide realistic avatars, so that you can have your avatar and you can collaborate and converse and have this sense of presence. Um, and a lot of companies are, investing a lot in this. This is Apple. Uh, this is Meta. Apple buys a VR company to put real faces on virtual avatars. Um, and just before going there, it's that creates a lot of invasion of privacy concerns, because your smart glasses eventually will know about your emotions before yourself know about your emotions, because these sensors can track your emotions better than your own brain by analyzing many different aspects of your eyes, of your skin, and so on, and with artificial intelligence, predict your emotions before you are fully aware of your own emotions, which is really interesting if you want to sell something, Um, but creates a few concerns for invasion of privacy. So we'll hear a little bit more about this in the future, I think. The various phases of smart glasses, that's the last slides. Um, well, what AR hardware for the metaverse? Well, you can implement different applications, such as on the lower end, contextual display based on a contextual engine, for example, Google's contextual engine, to provide contextual display to the user of the smart glasses. Flat apps such as monitor. So you can see on the second picture that that person has a keyboard and a mouse, but no monitor. But actually, that person has monitors, a few monitors in front of him or her, virtual monitors, and then pixel apps, which are really 3D gaming applications, and then scene apps. Scene apps are really interesting. SCENE, scene apps, where different applications are running at the same time, and then they talk to each other. And they talk to applications that are running on headsets of other participants in the world. And this is really the first step into the metaverse. So you have a few concepts of a few limits of weight of these smart glasses: 30, 45, 75, 150. These are not smart glasses anymore, they're goggles. 200 grams, this is a mixed reality headset, and then video see-through headset, 300 and over. Um, the power, very important. You can only dissipate about 1 watt or 2 watts on a pair of the smart glasses, whereas you can dissipate 6 to 8 watts on a headset, so you can add more sensors to it. Immersion will start with audio, such as Facebook Ray-Ban stories, up to monocular, then binocular, and eventually large field of view. Display lock is very important. In contextual display, there's no world locked hologram. So when you move your head around, the display moves around with you. You really want to have in next generation smart glasses a world locked hologram. When I say hologram, it's an abuse of language. It's a stereo display, basically. And eventually you want to have occlusions, spatial anchors in your and versus accommodation conflict mitigations also. The sensors will increase, and the apps will of course be more complex. And here you have a few examples on the last row. So elements of the metaverse, of course, includes video conferencing, but also social acceptability. And this is a little challenge that I sent to the optical engineers among you, sorry, before concluding. A key remaining challenge for consumer mixed reality or smart glass reality experience is social comfort. It's not so much, well, the comfort comes in 4 different declinations. Wearable comfort needs to be small, lightweight, and the center of gravity close to the center of gravity of your head. Vision comfort, we talked about the versus accommodation conflict, hard edge pixel occlusion, but also prescription integration. And then comes the social comfort. the comfort of yourself in a social surrounding with real people looking at you, and you shouldn't look like a steampunk, but you should look like a regular human being with regular pair of glasses. And the diffracted field through most of the diffractive, even wave optic that was bought for $500 million was not able to solve the problem of eye glow. Eye glow is really the diffracted field that comes out the waveguide the wrong direction. Um, so there's a display engine that couples the light in the waveguide, and the light should come to your eye. And the light comes to your eye, but with standard diffractive elements, 40% of the light goes to the world. So if you have an idea on how to design diffractive optics where the light is only extracted towards the eye, but not towards the world, without with a good transmission, well, you're up to a good start of becoming a billionaire. Um, and this is an example of a hybrid use case for mixed reality where there's a real person and a virtual person. And you don't want to have this. This is really what we have in HoloLens 2. This is the world side, and this is what you see when the display is on. You cannot see the eyes anymore. In a social setting, when you lose the contact with the eyes, you lose the contact with the person. And most of the diffractive waveguides provide this eye glow, which then obscurates the eyes of the wearer. And the severity of the eye glow is a function of the diffractive technology that is used. Okay, let's go to summary. We want to build an equitable, diverse, and inclusive metaverse experience, and not something like this. The future of, for example, of Microsoft HoloLens project, well, more equitable meetings for starters. I advise you to read that article online. Facebook also, I was happy that Facebook announced a $50 million research and partnership fund to build the metaverse responsibly. We also talked about a lot of invasion of privacy with sensors that will know your emotions better than you know your own emotions. So are we ready to provide a suitable hardware to the metaverse? Well, we have an obsolescence of current hardware, which is smartphone, which is end of life, about 10 years, 15 years old. And then the context, which is the post-pandemic, or should I say the pandemic, still. Universal use cases, we talked about it, human factors, development platforms such as OpenXR, MR cloud services such as Mesh for Microsoft, C3 from Magic Leap, and of course Metaverse, which is a universal concept. It's not linked to a company, certainly not linked to a company that's called Meta, but it's really a universal concept. Technological building blocks, we talked about this, processes, equipments, and material providers, readiness level of contract manufacturers, venture capital, corporate capital investment. We talked a lot about this, public investment, and I think that that concludes. And the conclusion is we're nearly ready, and every year we're closer to the ultimate hardware that will enable that vision of the metaverse as far as smart glasses and AR goggles are concerned. And I would like to thank the Université Jean Monnet and the Université de Lyon for inviting me, Yves and Pierre and the whole team, Cécile. And I would like to thank also SPIE and Google for allowing me to talk about this. So all the anything that I talked about today is public domain, and I will send a link to Yves to my slides, and if you want to review the slides later on, you'll be able to do so. Thank you.